This is a No Adam video.
Welcome everybody, we are group B41 and we'll be covering the topic of combinatorial proofs. So, a combinatorial proofs of an identity could be done using two methods. The first method is double counting. Using the double counting proof. And the second method would be using the bijective proof. So now allow me to explain to you guys what the double counting proof is and what the bijective proof is. So the double counting proof is the proof that uses counting arguments to prove that both sides of the identity count the same objects but in different ways. Whereas the bijective proof is based on showing that there is a bijection that occurs between the two sets of objects that are counted on both sides. Well, allow me to further elaborate. Double counting proof is a technique for showing that two expressions are equal by demonstrating that there are two ways of counting the size of one set. Whereas the bijective proof shows that there is a bijective function that goes between the two sets formed from n of r and n of n minus r, that there is a bijection that exists.
Alright, now let's actually look at a real example of a bijective proof. Recall that an R combination of a set with n elements, also known as C n comma r, is equal to n factorial over r factorial n minus r factorial. And using the bijective proof method, we're going to show that C of nr is perfectly equal to Cn n minus r. So first off, we're going to say that we have, for all integers n and all integers r, where r is between 0 and n. Suppose we now have a set S who has n elements. Alright, now let's consider a function that maps a subset of S to its complement. So for some subset of S, let's just call it A. And let's say that A has r elements in it. And recall that S has n elements in it. So the cardinality of the complement of this set would then have to be n minus r. And so now we've got a function that maps a subset of S, A, to A complement. And this is a bijection between these two subsets where A has r elements and A complement has n minus r elements. And so it follows that the identity that I originally presented, which was CNR is equal to Cn n minus r, follows. Because when there's a bijection between two finite sets, the two sets must have the same number of elements. So recall a bijection between A and A complement can only be a bijection if it's onto and one-to-one. So if A complement somehow had an extra element, we couldn't cover the entire codomain, and that wouldn't be a bijection, so it follows that this is a bijection. We can reformulate this argument as a double counting proof. By definition, the number of subsets of S with R elements equals C and R for some subset A of S. And this subset A of S is also determined by specifying which elements are not in A, which is, by definition, A complement, which is a subset of S. And that is equal to C of n minus r. Alright, to provide some context into this argument, let's consider the horrible occurrence of whale killing in in our world today. Let's say that for every 10 whales, 1 is killed by a whaling vessel. And so that would mean n equals 10. And we're looking for r equal to 1. We're looking for the number of combinations, the number of different whales that could be killed in a set of 10, but just one whale. So this is C of 10 comma 1, which is equal to 10 factorial, 1 factorial, 10 minus 1 factorial, which simplifies to simply 10. So that means that there's 10 combinations of whales killed from a set of 10, if you were to just kill one whale out of the set. So let's say that we have a set and there's 10 whales, and let's say there's Bob and Betty and Brian, dot, 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 all the way to 10. Let's, from the set, and this is equal to 10, cardinality, one combination would simply be Bob, where Betty, Brian, and so go off free, and Bob is sadly killed. But another combination would arrive from when Bob is alive and Betty gets killed. Now, this is the same thing as saying how many combinations of whales aren't killed from a set of 10. And so we knew R was 1, so 1 whale is killed out of every set of 10. So this is the same thing as saying C of 10, 10 whales, 10 minus 1, which equals 9. So C of 10, comma 9, which simplifies down to 10 factorial, 9 factorial, 10 minus 9 factorial, which is 10 factorial over 9 factorial, which gives us 10. So this is interesting because if you recall, we said that 1 whale out of 10 is killed, and there's 10 combinations of that. There's one for Bob, there's one for Betty, there's one for Brian, and so on. Likewise, the complement of this subset of combinations is C of 10 n minus r, which was C of 10, 9, which came out to be 10 combinations again, which means that in our first example, we said Bob died, sadly, and we had Betty, and so on, 9 other whales. And then, let's say the next combination involves Betty dying, and Bob would be in this new set, minus Betty, and the rest of the whales. You can keep doing this for n, which is 10, and you'd reach the same conclusion, which was there's 10 combinations of the whales that die, and there's 10 combinations of the whales that don't die. They are related, and you can form a bijection between these sets, like I discussed earlier, and that is the idea behind a combinatorial proof.
Let's take a look at the equation of the summation from k equals 0 to n of n choose k equals 2 to the n. We can prove this statement with a double counting proof. So let's say we have some set S with cardinality n. Then we know that the cardinality of the power set of S is 2 to the n. Let's take a look at all of the subsets. There's going to be a subset with 0 elements, a subset with 1 element, subsets with 2 elements, all the way to n elements. So if we count them, there's n choose 0 subsets with 0 elements. And then n choose 1 subsets with 1 element, and choose 2 subsets with 2 elements, and so on all the way to n choose n. So we can easily write that as a summation from k equals 0 to n of n choose k. So now we know that counts the total number of subsets of a set with n elements. But we knew from before that that's also 2 to the n, showing that this equals 2 to the n. These kinds of proofs are often simpler and more intuitive than other kinds of proofs. For more screencasts on discrete math topics, visit noatom.com.